Okay, let's develop the MATLAB code of another direct method to solve linear systems, and this time the method is going to be Gauss-Jordan method. First of all, let's understand the Gauss-Jordan method by taking an example of 3 cross 3 linear system. So I have 3 linear equations and this is the matrix representation of those equations. Like A is going to be my coefficient matrix, X matrix of unknowns, and B the right hand side vector, also known as source vector. Like Gauss elimination method, in Gauss-Jordan method the step number 1 is to write the augmented matrix, and in augmented matrix we just write the source vector with the coefficient matrix in one matrix like this. So you can see on the right hand side I have source vector also involved, and this matrix is known as augmented matrix A B, since A is augmented with B. Okay, so the next step is going to be make the each pivot entry 1 and make the entries below and above that pivot entry 0. For this, as you can see that my first pivot entry is 10 because of its pivot position. Now my first goal is to make this 10 1. So I will simply divide the whole first row with 10. Like this is the restriction of row operation. In real, we are actually dividing the whole equation with 10, right? So I will divide the complete first row with the pivot position, which is 10, and R1 divided by 10 will give me something like this in the first row. So now the next target is to make the entries below and above the pivot position 0. So I can only see the entries below this pivot position, so I want to make them 0. So first, for to make this 3 0, I will just find the multiplier, which is going to be this 3 actually in Gauss-Jordan method. So I will subtract row 2 from multipliers time row 1. This is again a row operation. So after doing this, I will get 0 at this position and the remaining entries of row 2 will also change, but row 1 remains the same. Now for next step, I want to make this one entry 0, so this 1 will become the multiplier, and now row 3 will be subtracted from multipliers time row 1, and I will get this entry as 0, and the remaining entries of row 3 will also change. Okay, that's it for the first pivot position. I made the first pivot entries 1 and the entries below it 0. Now I have to identify the second pivot position and then the pivot entry. This time this pivot position is the second row and the pivot entry is 9.1. So again, according to row operation, I will divide the whole row 2 with this pivot entry, which is 9.1 actually, and this will give me 1 at the pivot position, and all the remaining entries will also change. Now the next step is to make this 0.3 and this 1.70. So first I will pick 0.3. For this, 0.3 will be my multiplier and row 1 will be subtracted from multipliers time row 2 to give me 0 at this position, and all the entries remaining will also change in the row 1, but row 2 remains the same. Same goes for making this 1.7 as 0. So 1.7 will come as my multiplier. Now row 3, since 1.7 is in row 3 minus multipliers time pivot row, and I will get 0 above and below this pivot position, and my pivot entry is 1. So next pivot position is going to be this, and this is my pivot entry. Now I want to make this pivot entry 1. I will divide the row 3 with this entry, and after doing this I will get 1 at this position. Now I want to make the above entry 0. First, if I want to make this 0, this will be my multiplier, and after doing row 1 minus multipliers time pivot row, I will get 0 here, and this entry will also change. And finally, my multiplier is this, because I want to make it 0. So this will come as multiplier here, and since it is in row 2, so row 2 minus multipliers times the pivot row, and I will get 1 at the pivot position and zeros above and below those pivot positions. Since we do not have another row, so we have to stop here. So after doing this, the last column is nothing but my solution. As you can see, I have eliminated the variables x2 and x3 from the first row, so only x1 come as 1. Also in the row 2, I'm only left with x2, so x2 is simply 2 in this case, and in row 3 I am only left with x3 because I eliminated all the other variables, and x3 is simply 3. So this is the solution of the given system. So this is how Gauss-Jordan method works. Now our task is to develop the MATLAB code of Gauss-Jordan method. So let me open the MATLAB for this purpose, and this is the main window of MATLAB, and I am going to make a new script file in which I will write the code of Gauss-Jordan method. Okay, so first of all, there will be my ingredients, like I have to put A and B matrix in order to start Gauss-Jordan method. Like these are the basic ingredients. Without A and B matrix, there is nothing on which I am going to apply Gauss-Jordan method. So these are my basic ingredients, and I am going to take input from user. So I will run my code and then I will input these matrices. So the next step after this is going to be how to identify the number of unknowns that I am going to get from A and B matrix. So simply the length of B can tell me how many unknowns I am going to have. Like if I go to my example, I have three entries in B because my system is 3 cross 3. So length of B command will simply tell me how many entries are in B, and I will store that number into capital N. So in capital N, I will actually have how many number of unknowns I have. So then I have to introduce my matrix of unknowns. Initial entries of my matrix of unknowns will be zeros, since I am using the command of zeros, and the dimension of my matrix of unknowns will be n cross 1. As you can see in the document that if B is 3 cross 1, my matrix of unknown will also be a 3 cross 1 matrix or vector. So according to the first step of Gauss-Jordan method, I have to augment A and B, and this is how I will do it. Like I'm storing this thing in AUG augmented, and I will simply write square bracket A space B matrix to augment B with A. I'm also putting the semicolons on the things that I don't want to see when my code runs. So my A matrix will be given by the user, B also by the user, and this is how I will find my augmented matrix, like A is augmented with B. Next, I have to apply Gauss-Jordan method. To be more precise, I want to make each pivot entry 1 and the entries below and above that pivot entry as zeros. So for this, I will use the nested for loops. My first loop or the outer loop is going to be for columns. That's why I'm using the J for it. Like there is no restriction on it, just J makes sense. We use J for columns usually and I for rows. So my J will go from 1 to number of unknowns. So number of unknowns are stored in capital N, and my inner loop will start from I equals to 1 to n2, and this is for rows. I have to end the inner loop and then I have to end the outer loop. So let me write it here, like this is for columns and this is for rows. Okay, so the first step is I make the pivot entry 1. As you can see here, first of all I make the pivot entry 1 whenever I enter into the new column, and then I make the entries below and above that pivot entry 0. So when I will enter into the column 1, like this is my column, so my first task is going to be make this entry 1, and then I will take care of all the other entries in this column, like this entry and this entry, to make them 0. Okay, so to make the pivot entry 1, what I do is to divide the pivot row with that pivot entry. Okay, and the pivot entry always comes in the diagonal for a consistent system. So this is how I will do it. Whenever I enter into a new column, I will divide, I will update the row. How? I will divide that complete row with the pivot entry. So like if I am in the first column, like j will be 1, so I will divide the jth row, I will update the jth row as I divide the jth row with ajj. So for j is equal to 1, my first row will be updated as first row divided by a11, like we have here, like first row divided by a11. Let me show you this thing for the second pivot entry. So for second pivot entry, I am dividing the second row with a22, and for last third row with a33. So this makes sense. When j will be 1, a first row will be updated as a first row divided by a11. When j will be 2, a second row will be updated as a second row divided by a22, and same for the third row. Okay, after doing this, after making that entry 1, I have to make the entries below and above it as 0. So the inner loop will take care of this. Okay, let's learn the concept from here. Like if I want to make the entries below first pivot entry 0, I will only make changes into the row 2 and row 3. I'm doing this for first pivot entry, and I will only make the changes in row 2 since I want to make the 0 entry in row 2 and row 3. Okay, when I will be in the second pivot entry, so I will only make changes in row 1 and row 3 since I am in the second pivot entry and I don't want to make that pivot entry 0. And if I am in the third pivot entry, so I will not play with the 3, I will only make changes or make zeros in row 1 and row 2. So in coding, I will proceed further if I is not equal to j. So I will apply the row operations to make the entry 0 only if I is not equal to j. Clearly for j is equal to 1, I will get inside this if and only if I is not equal to j. So the condition of if will allow me to enter in this body whenever I is not equal to j. So to make the entries zeros, my first step is to find the multiplier. Like here, my multiplier is simply that entry which I want to make 0. The position of this entry is A21. I am in first column, so it is 21, and the position of the next entry is going to be 31. I am in column 1 and the next row of it. So simply my multiplier in general is going to be A, I, comma J entry. So for column 1, when J will be fixed as 1, I will move in this if when I will be 2 and 3, since I is not equal to J is the condition to get in this body. Now the first time when I will get into this body, A21 will be stored as a multiplier. After finding the multiplier, the next step is to update that row. So that row of augmented matrix, sorry, here I should write AUG. Okay, so the ith row of my augmented matrix will be updated as augmented matrix ith row subtract multipliers time augmented matrix pivot row. So pivot row is basically the fixed column. So if we dry run this in mind, for j is equal to 1, we only enter in this if when I is 2. For I is equal to 2, M is going to be augmented matrix entry 2, 1, and the second row of augmented matrix will be updated as second row subtract multipliers time aj1, j is fixed as 1, augmented matrix first row. So you can see it from here, like R2 will be subtracted from multipliers times R1 and R3 will be subtracted from multipliers times R1. And in the next step, for second pivot entry, R1 will be subtracted from multipliers time pivot row. In that case, in J we will have 2, and that's how this is going to work. And that's it. We developed the MATLAB code of Gauss-Jordan method in just 15 lines. So let me run this code. To save it, I will write Gauss-Jordan and I will save it on my desktop. Okay. So I'm running it and he is demanding a coefficient matrix from me. I will enter the same matrix to first verify my code. So my matrix is going to be 10, 3, 1, 3, 10, 2. This is my given matrix, coefficient matrix, and my source vector is going to be this. So you can see you can just verify these multipliers and all these steps from that document, but here the final goal was to get the pivot entries 1 and the entries below pivot and above pivot zeros, and the final column is my solution. But this code is general, like I can solve an n cross n system. For example, if I want to solve a system of bigger dimension, I'm giving a random system of 8 cross 8 whose entry will start from 1 to 10, and this is my A matrix in this case, and my source vector is going to be of course 8 cross 1 in this case. So here it is. And you can see this code converted the 8 cross 8 system into its Gauss-Jordan form, and finally I got the solution of this system in the final column. Okay, let's just verify this code from the built-in command of MATLAB, and the built-in command of MATLAB to perform Gauss-Jordan method is RREF. So first I am just augmenting this A and B that I just used in my code. So I augmented the A and B and stored them in C, and I am applying the built-in command of MATLAB, which is RREF on C, and Here you can see I got some solution, and let's see what I got from my code and then verify them. So from my code it is from MATLAB code it is 1.3234, and from my code it is 1.3234, and you can also verify all the other unknowns. That's it. Thank you for watching this video. If you are new on this channel, just hit the subscribe button. See you in next video. Bye bye.